Chapter 1.2.1 Nodes. Kubernetes is a system that manages workloads by placing containers into pods, which run on nodes. Nodes can be virtual or physical machines and are managed by the control plane. Each node contains the services needed to run pods. A cluster typically has multiple nodes, but in some cases there may be only one node, such as in a learning or resource-limited environment. Components on a node include the kubelet, container runtime, and kube proxy, which are essential for running containers. Management. Nodes can be added to the API server in two main ways: through self-registration by the kubelet on a node or manually added by a human user. Once a node object is created, the control plane checks its validity and ensures that the kubelet has registered to the API server. If the node is healthy and all necessary services are running, it is eligible to run a pod. If the node is not healthy, it is ignored until it becomes healthy. The name of a node object must be a valid DNS subdomain name, and uniqueness is required as two nodes cannot have the same name at the same time. Self-registration of nodes occurs when the kubelet flag register node is set to true, causing the kubelet to register itself with the API server. This is the preferred method and is used by most distributions. The kubelet is started with certain options such as kubeconfig to authenticate with the API server, cloud provider to read metadata about itself, register node to automatically register with the server, and other options related to node IP addresses, labels, and status update frequency. Manual node administration can be done using kubectl, regardless of the self-registration setting. Nodes can be created, modified, and marked as unschedulable using this method. Labels on nodes can be used in conjunction with node selectors on pods to control scheduling. Marking a node as unschedulable prevents new pods from being placed on it, but existing pods remain unaffected. This is useful for pre-reboot maintenance tasks. Daemon sets, which provide node local services, can tolerate being run on unschedulable nodes. In addition, when updating node configuration, it is recommended to re-register the node with the API server to ensure changes take effect. This is important for maintaining consistency and avoiding issues with pods that may be affected by node configuration changes. Overall, proper management of node objects is essential for maintaining a healthy and efficient Kubernetes cluster. Node status. A node status includes addresses, conditions, capacity, and allocatable info. Use kubectl to view a node status and additional details. Refer to the node status documentation for more information on how to access and interpret this information. Node heartbeats. Heartbeats sent by Kubernetes nodes are crucial for determining node availability and responding to failures. There are two forms of heartbeats for nodes: updates to the .status of a node and lease objects within the kube node lease namespace. Each node has an associated lease object to help manage cluster health and availability. Node controller. The node controller in Kubernetes is a key component of the control plane that manages various aspects of nodes. It has multiple roles in a node's lifecycle, including assigning CIDR blocks, keeping lists of nodes up to date with cloud provider information, and monitoring node health. The node controller is responsible for updating the ready condition of nodes, triggering API-initiated evictions for unreachable nodes, and setting eviction rates. The eviction behavior of the node controller changes based on the health of nodes in specific availability zones, with lower eviction rates when a zone has a high percentage of unhealthy nodes. The node controller also takes into account node taints and adds corresponding taints for node problems to prevent scheduling pods onto unhealthy nodes. The goal of these policies is to ensure that workloads can be shifted to healthy zones during outages and that evictions are done in a controlled manner to prevent disruption to the cluster. In cases where all zones or all nodes are unhealthy, the node controller may pause evictions to prevent further issues. Overall, the node controller plays a critical role in managing the health and availability of nodes in a Kubernetes cluster. Resource capacity tracking. Node objects in Kubernetes store information about the resource capacity of a node, such as available memory and CPU count. Nodes that self-register provide their capacity data during registration, while manually added nodes require capacity information to be set at the time of addition. The Kubernetes scheduler ensures that there are sufficient resources for all pods on a node by checking that the sum of container requests does not exceed the node's capacity. This sum includes all containers managed by the kubelet, but excludes containers started directly by the container runtime and processes running outside of the kubelet's control. It is suggested to reserve resources for system daemons if needed. In Kubernetes v1227 stable, with the Topology Manager feature gate enabled, Kubelet can utilize topology hints for resource assignment decisions. More information on controlling topology management policies on a node can be found in the documentation. Swap memory management. In Kubernetes v1.3 beta, the node swap feature allows for enabling swap on a node with specific configurations required to control swap behavior. By default, swap is disabled, but it can be enabled by setting the fail swap on configuration setting to false. Pods can utilize swap by configuring the swap behavior setting in the kubelet config with options for no swap, default, limited swap, and specifying swap behavior for different QoS pods. Kubernetes data may be swapped to disk when the memory swap feature is turned on, potentially impacting secret objects stored in TMPFS. The swap limit calculation is based on the container's memory request, node total memory, and total available swap memory for pods. Containers within burstable QoS pods can opt out of swap usage by setting memory requests equal to memory limits. Swap is only supported with cgroup v2, not cgroup v1. For more details on configuring and testing swap functionality in Kubernetes 1.30 beta, refer to the blog post on node swap and associated design proposals.